James Webb found a planet with 99.7% chance of life, December 2023. A team at Cambridge University stares at data that shouldn't exist. Light from a planet 120 light-years away, filtered through an alien atmosphere, analyzed by humanity's most powerful telescope. The James Webb Space Telescope has detected something extraordinary on K2-18b, a super-Earth orbiting a red dwarf star in the constellation Leo. The numbers are staggering: a planet 8.6 times Earth's mass, wrapped in a hydrogen-rich atmosphere, with temperatures that could allow liquid water to exist. But that's not what made astronomer Niku Madhusudan's hands tremble. It's what Webb found in that atmosphere, a chemical signature that, on Earth, only living things produce. Dimethyl sulfide, 3 words that might rewrite everything we know about our place in the universe. On our planet, this molecule comes exclusively from biological processes. Phytoplankton in the oceans create it. Marine bacteria pump it into the air. No known geological process, no volcanic activity, no chemical reaction has ever been observed making this molecule without life. The detection carried a confidence level that astronomers rarely see, 99.7%. In a field where uncertainty is the norm and discoveries often crumble under scrutiny, this number represents something profound. 3 sigma detection, the same statistical threshold used to discover gravitational waves and confirm the Higgs boson. But here's what makes this discovery genuinely revolutionary. We're not just detecting a potentially habitable planet. We may be detecting a planet that's actually inhabited. There's a fundamental difference between those 2 statements, and that difference could end humanity's cosmic loneliness forever. K2-18b orbits in what astronomers call the habitable zone, that Goldilocks region where a planet isn't too hot, isn't too cold, but potentially just right for liquid water. Webb's instruments detected not just water vapor, but methane and carbon dioxide, a cocktail of molecules that, when combined with dimethyl sulfide, paints a picture of active chemistry that looks remarkably biological. The planet completes an orbit around its star every 33 days. It's tidally locked, meaning one side permanently faces its sun, while the other remains in eternal darkness. Its star, K2-18, is a red dwarf, smaller and cooler than our sun, but far more stable, potentially burning for trillions of years, while our sun will eventually expand and consume Earth. This isn't Earth 2.0, it's something stranger and potentially more significant. A world so alien we never thought to look for life there. A hydrogen atmosphere instead of nitrogen and oxygen. Surface gravity 3 times stronger than Earth's, conditions so different from our own planet that they challenge every assumption about where life can exist. The implications ripple outward like light from a distant star. If life emerged on K2-18b in conditions nothing like Earth, then the universe might be teeming with biology in places we dismissed as inhospitable. Red dwarf stars make up 75% of all stars in the galaxy. If their planets can harbor life, the number of potentially inhabited worlds jumps from millions to billions. But we need to be clear, this is not confirmed. The scientific community is divided. Some researchers argue the dimethyl sulfide signal could be instrumental noise, data artifacts, or misidentified spectral lines. Others point to the molecule's fragility. It breaks down quickly in atmospheres, so its presence demands an active source constantly replenishing it. The truth is, we're standing at the threshold of the greatest discovery in human history. Either we've detected the chemical signature of alien life 120 light-years away, or we've discovered how maddeningly difficult it is to be certain about anything across interstellar distances. What we do know is this: the universe just became a lot more interesting. For decades, astronomers searched for Earth's twin, a rocky planet, roughly our size, orbiting a sun-like star at just the right distance for liquid water. We built our entire search for extraterrestrial life around this assumption. Life needs an Earth clone to exist. K2-18b destroyed that assumption completely. This world is nothing like Earth. It's a super-Earth, a category of planet that doesn't exist in our solar system. With 8.6 times our planet's mass, it sits in the gap between rocky worlds like Earth and ice giants like Neptune. For years, scientists dismissed these planets, as uninhabitable gas balls, too massive to support life as we know it. But K2-18b forced astronomers to completely reimagine what a habitable world looks like. The planet's atmosphere is dominated by hydrogen and helium, the same gases that make up Jupiter and Saturn. On Earth, hydrogen is a trace gas, barely detectable. On K2-18b, hydrogen comprises the vast majority of the atmospheric envelope. This changes everything about how we think about habitability. A hydrogen atmosphere creates what scientists call a greenhouse effect, but not the runaway disaster we see on Venus. Instead, the hydrogen acts as a perfect insulator, trapping heat in a way that could maintain stable temperatures across the entire planet. Even the night side, which never sees sunlight due to tidal locking, could remain warm enough for liquid water. The planet's mass creates surface gravity nearly 3 times stronger than Earth's. A person weighing 150 pounds here would weigh over 400 pounds on K2-18b. That sounds like a deal breaker for life, but the intense gravity actually provides crucial advantages. It holds the atmosphere in place with an iron grip, preventing it from bleeding away into space the way Mars lost its atmosphere billions of years ago. K2-18b's star adds another layer to this alien environment. K2-18 is a red dwarf, a type of star that makes up 3/4 of all stars in the Milky Way. These stars are smaller and cooler than our Sun, but they have one extraordinary advantage: longevity. While our Sun will burn for about 10 billion years total, red dwarfs can shine for trillions of years, longer than the current age of the universe. This matters because evolution takes time. On Earth, simple bacteria appeared relatively quickly, but complex multicellular life took nearly 4 billion years to develop. If K2-18b has even a fraction of the time available around its red dwarf star, life there could have reached levels of complexity that make Earth's biosphere look primitive. The planet orbits close to its star, completing one orbit every 33 days. But because K2-18 is cooler than our Sun, this close orbit places the planet in the habitable zone, that sweet spot where temperatures allow liquid water to exist. It's a cosmic coincidence that K2-18b receives almost exactly the same amount of energy per square meter as Earth receives from our Sun, despite being in such a different stellar system. The tidal locking creates a permanent day side and permanent night side. On Earth, we'd consider this catastrophic for life. But K2-18b's thick atmosphere could redistribute heat so efficiently that both sides maintain habitable temperatures. The result is a world with 2 distinct environments, eternal day and eternal night, each potentially hosting different forms of life adapted to radically different conditions. What makes K2-18b truly revolutionary is that it represents an entirely new category of potentially habitable worlds. If life can exist on a hydrogen-rich super-Earth, orbiting a red dwarf star, then we need to expand our search parameters dramatically. We're not looking for Earth's twin anymore. We're looking for Earth's strange cousins, worlds that might be even better suited for life precisely because they're so different from our own planet. The universe just revealed that it's far more creative than we imagined. The James Webb Space Telescope isn't just humanity's most powerful space observatory. It's a time machine that peers deeper into the cosmos than any instrument ever built, and it sees the universe in a way human eyes never could. Webb operates in infrared light, wavelengths longer than visible light but shorter than radio waves. To our eyes, infrared is invisible, but to Webb, it's the key that unlocks the chemical secrets of distant worlds. When planets pass in front of their stars, a tiny fraction of starlight filters through their atmospheres before reaching Earth. Different molecules absorb specific wavelengths of infrared light, creating unique fingerprints that Webb can detect with extraordinary precision. The telescope floats at a point called L2, roughly 1 million miles from Earth, where the gravitational pulls of Earth and the Sun balance perfectly. Here, Webb exists in perpetual shadow, its massive sun shield blocking heat and light to keep its instruments colder than the surface of Pluto. This extreme cold is essential. If the telescope were warm, its own heat would overwhelm the faint infrared signals it's trying to detect from distant planets. Webb's primary mirror stretches 21 feet across, composed of 18 hexagonal segments coated with a microscopic layer of gold. Gold reflects infrared light with exceptional efficiency, and each mirror segment is aligned with nanometer precision to work together as a single, perfect optical surface. When these segments function in harmony, Webb can detect the infrared glow of a bumblebee at the distance of the Moon. But detecting molecules on K2-18b required Webb to operate at the absolute limits of its capabilities. The challenge is almost incomprehensible. The planet is 120 light-years away, and the star it orbits is billions of times brighter than the planet itself. It's like trying to see a firefly hovering next to a searchlight from 1,000 miles away, then analyzing the specific color of that firefly's glow. The technique is called transmission spectroscopy. When K2-18b passes in front of its star, from our perspective, the star's light shines through the planet's atmosphere. Molecules in that atmosphere absorb specific wavelengths, creating dark lines in the spectrum, the chemical fingerprint Webb can read. But the signal is extraordinarily faint. Webb had to observe multiple transits over several months, collecting photons one by one, building up enough data to detect molecules present in parts per billion. The detection of dimethyl sulfide pushed this technique to its breaking point. The molecule produces an infrared signature so subtle that advanced algorithms had to analyze millions of data points, searching for patterns that would be invisible to human observers. The entire process required artificial intelligence systems trained to distinguish genuine molecular signatures from instrumental noise and random fluctuations. Webb's infrared vision also allowed it to measure K2-18b's temperature with remarkable accuracy. By analyzing the thermal emission from the planet's day side, astronomers determined that surface temperatures likely hover around 120 degrees Fahrenheit, warm enough for liquid water but cool enough to prevent complete evaporation. This temperature measurement, accurate across 120 light-years, represents one of the most precise environmental readings ever made of an exoplanet. The telescope's coronagraph technology plays a crucial role in these observations. Originally designed to block starlight and reveal faint objects in the glare, the coronagraph uses precisely shaped masks to eliminate the overwhelming brightness of the star while allowing light from the planet's atmosphere to pass through. The tolerances are so extreme that a misalignment of just a few billionths of a meter would ruin the entire observation. What makes Webb truly revolutionary is that it's not just detecting the presence of molecules, it's measuring their abundance, their distribution throughout the atmosphere, and how they interact with each other. This level of detail allows astronomers to distinguish between lifeless chemical processes and the complex, out-of-equilibrium chemistry that characterizes living worlds. Webb has fundamentally changed our relationship with the cosmos. We're no longer just wondering if life exists elsewhere. We're actively reading the chemical signatures that might prove it does. Dimethyl sulfide. The name sounds like something from a chemistry textbook, but these three words represent the most controversial and potentially revolutionary discovery in the history of astronomy. On Earth, this molecule has one defining characteristic. Life makes it, and only life makes it. Phytoplankton in the oceans produce dimethyl sulfide as they metabolize sulfur compounds. Marine bacteria generate it as a byproduct of breaking down organic matter. Some plants release it into the atmosphere. But no geological process, no volcanic eruption, no non-biological chemical reaction has ever been observed creating this molecule. That's what makes its potential detection on K2-18b so extraordinary and so contentious. When Niku Madhusudan's team at Cambridge analyzed Webb's spectroscopic data, they found an absorption feature that matched the infrared signature of dimethyl sulfide. The signal appeared at exactly the wavelengths where this molecule absorbs light, and it was strong enough to suggest significant concentrations in the planet's atmosphere. But here's where the story gets complicated. Other research teams looked at the same data and aren't convinced. Some argue the signal could be carbon disulfide, a related molecule that can form through non-biological processes. Others suggest it might be an instrumental artifact, a ghost signal created by the way Webb's instruments process light. A few researchers point out that the spectral lines overlap with other molecules, making definitive identification extremely difficult. This is how science actually works. It's messy, uncertain, and filled with legitimate disagreement. The 99.7% confidence level refers to the statistical significance of the signal itself, that something is absorbing light at those wavelengths. But what that something is remains hotly debated. The molecule's chemical structure adds to both the intrigue and the controversy. Dimethyl sulfide consists of a sulfur atom bonded to two methyl groups, carbon atoms surrounded by hydrogen. Creating this structure requires specific conditions and, on Earth at least, specific enzymes that evolved over billions of years as part of the sulfur cycle. If the detection is real and it is dimethyl sulfide, the implications are staggering. The concentrations would have to be enormous to be detectable from 120 light-years away. We're not talking about trace amounts produced by scattered organisms. We're talking about planetary-scale biological activity. A biosphere so vast and productive that it's fundamentally altering the atmospheric chemistry of an entire world. Dimethyl sulfide is also highly reactive. In Earth's atmosphere, it breaks down within days when exposed to ultraviolet radiation and oxygen. Its presence demands a constant source actively replenishing it. This is actually a strength of the biosignature argument. If the molecule is there, something must be continuously producing it in massive quantities. But the scientific community isn't ready to declare victory. The spectroscopic features are at the edge of Webb's detection capabilities. The signal-to-noise ratio is low, meaning the data contains a lot of random fluctuations that could be mistaken for real signals. Multiple research groups are currently working on independent analyses, trying to confirm or refute the detection. Some scientists are calling for follow-up observations with different instruments and techniques. Others want to see if the signal persists in future transits of K2-18b. A few researchers are developing new laboratory experiments to better understand how dimethyl sulfide behaves under the exotic conditions of a hydrogen-rich atmosphere. The controversy highlights a fundamental challenge in astrobiology. Proving life exists on a world we can never visit requires extraordinary evidence. We can't send a probe to K2-18b, we can't collect samples, we can't study organisms in a laboratory. All we have is starlight filtered through an alien atmosphere, analyzed by instruments operating at the absolute limits of their capabilities. Whether the dimethyl sulfide detection holds up or not, it's already changed the field. Astronomers now know that Webb can potentially detect biosignatures on distant worlds. The next generation of observations will be even more sensitive, targeting multiple molecules and looking for the complex chemical patterns that characterize living worlds. We're learning to read the universe's chemical language, one molecule at a time. The atmosphere of K2-18b tells a story written in molecules: water vapor, methane, carbon dioxide, and possibly dimethyl sulfide. Each one is a clue, but it's the combination that makes this world so intriguing. On Earth, this particular mixture of gases creates what scientists call chemical disequilibrium, and it's one of the most powerful signatures of life. Chemical equilibrium is what happens when molecules reach a stable state and stop reacting with each other. A lifeless planet should eventually reach this equilibrium, creating an atmosphere that doesn't change over geological timescales. But Earth's atmosphere is wildly out of equilibrium. We have oxygen and methane coexisting, even though they should react with each other and disappear. The only reason they persist is that living organisms constantly produce both gases, maintaining the chemical imbalance. K2-18b shows similar signs of disequilibrium. Webb detected methane and carbon dioxide together in concentrations that suggest active chemistry. In a hydrogen-rich atmosphere, methane should be relatively stable, but the presence of other molecules creates possibilities for reactions that either produce or consume it. If biological processes are involved, they could be maintaining specific ratios of these gases. Water vapor is perhaps the most important detection. Webb found clear evidence of H2O molecules absorbing infrared light as it passed through K2-18b's atmosphere. This confirms that water, the universal solvent essential for life as we know it, exists on this world in significant quantities, but the water on K2-18b isn't behaving like water on Earth. In a hydrogen-rich atmosphere, water molecules interact with hydrogen gas in ways that change their properties. The mixture can remain liquid across a much wider range of temperatures and pressures than pure water. This hydrogen-enriched water could theoretically support biochemistry that uses hydrogen as an energy source. Organisms that literally breathe the water itself while extracting energy from dissolved gases. The methane detection adds another layer of complexity. On Earth, methane is overwhelmingly biological in origin. Bacteria and wetlands produce it. Microorganisms in animal digestive systems create it. Even termites generate methane as they consume wood. Geological sources exist, volcanic vents, and deep earth processes can release methane, but they're minor compared to biological production. Methane is also highly reactive and breaks down quickly in most atmospheres. On Earth, methane has an atmospheric lifetime of about a decade before it's destroyed by chemical reactions. Its presence in K2-18b's atmosphere means something is actively producing it, whether that's biological processes, geological activity, or atmospheric chemistry we don't fully understand yet. Carbon dioxide provides context for understanding the planet's carbon cycle. On Earth, CO2 is consumed by photosynthetic organisms and released by respiration and decomposition. The levels fluctuate with the seasons as plants grow and die. K2-18b's carbon dioxide could indicate similar biological cycles, or it could simply be outgassing from the planet's interior. What makes the chemical cocktail on K2-18b so compelling isn't any single molecule, it's the pattern. The combination of water, methane, carbon dioxide, and possibly dimethyl sulfide creates a signature that looks remarkably similar to what you'd expect from a biologically active world. But it's not proof. Chemistry is complex, and we're still discovering non-biological processes that can create surprisingly lifelike chemical signatures. The hydrogen atmosphere itself changes the rules of chemistry. Reactions that would be impossible on Earth might be common on K2-18b. Molecules that would be unstable in our atmosphere might persist there. The entire field of astrochemistry is being rewritten as we study these exotic environments. Some researchers are exploring whether K2-18b could host what they call Hycean life, organisms adapted to hydrogen-rich oceans. These hypothetical ecosystems would use fundamentally different metabolic pathways than Earth life, potentially breathing hydrogen and metabolizing compounds that would be toxic in our biosphere. The atmospheric chemistry of K2-18b represents a puzzle we're only beginning to solve. Each new observation adds pieces, but the complete picture remains tantalizingly out of reach. What we do know is that this world's atmosphere is doing something interesting, whether that's biology or exotic chemistry. We're witnessing processes that challenge everything we thought we knew about planetary atmospheres. Beneath K2-18b's hydrogen-rich atmosphere might lie an ocean unlike anything in our solar system. Not pure water, but a solution of water mixed with dissolved hydrogen under pressures that would crush any Earth-based submarine. This is the ocean world hypothesis, and it's reshaping how we think about habitability. The concept emerged from computer models trying to explain K2-18b's density. The planet is too dense to be a pure gas giant like Neptune, but not dense enough to be solid rock like Earth. The most likely explanation is that K2-18b has a rocky core surrounded by a mantle of high-pressure water ice, topped by a deep liquid ocean, all wrapped in that thick hydrogen atmosphere. This ocean could be hundreds of miles deep, far deeper than any ocean on Earth. Our deepest ocean trenches reach about 7 miles down. K2-18b's ocean might extend 10 times deeper, creating an aquatic environment of staggering volume. If this ocean exists, it contains more water than all of Earth's oceans combined, multiplied 1,000 times over. But this isn't ordinary water. At depth, the pressure becomes so intense that water takes on exotic properties. Scientists call it hot ice, water that remains solid despite being hundreds of degrees above the normal boiling point, compressed by the immense weight of the ocean above it. This high-pressure ice forms a boundary between the planet's rocky interior and the liquid ocean. Near the surface, where pressures are lower, the water would be more familiar, though still radically different from Earth's oceans. The hydrogen from the atmosphere dissolves into the water, creating a solution that remains liquid across a much wider temperature range than pure water. This hydrogen-enriched ocean could support chemistry that's impossible on Earth. Here's where biology becomes possible. On Earth, some of the most extreme life forms exist in deep ocean environments where sunlight never reaches. These organisms use chemical energy instead of light, extracting energy from hydrogen, methane, and other compounds seeping from hydrothermal vents. They prove that life doesn't need photosynthesis, it can run on chemistry alone. K2-18b's ocean could be a paradise for chemosynthetic life. If the ocean contains dissolved hydrogen, methane, and other energy-rich compounds, organisms could metabolize these substances directly. They wouldn't need sunlight, they wouldn't need oxygen, they could exist in total darkness, powered by the planet's own chemistry. The ocean hypothesis also solves a critical problem for long-term habitability. Planets slowly lose their atmospheres to space over billions of years. But if K2-18b has a vast ocean saturated with dissolved hydrogen, that ocean acts as an atmospheric reservoir. As hydrogen escapes to space, more dissolves out of the ocean to replace it, potentially maintaining a stable atmosphere for trillions of years. The interface between ocean and atmosphere creates another potentially habitable zone. On Earth, our ocean surfaces teem with life. Phytoplankton, bacteria, and countless other organisms that form the base of the marine food web. K2-18b's ocean surface, where water meets hydrogen atmosphere, could host similar ecosystems adapted to that alien chemistry. Temperature gradients in the ocean create another possibility. The deep ocean, warmed by the planet's internal heat, might be significantly warmer than the surface layers. This temperature difference could drive convection currents that mix nutrients and energy-rich compounds throughout the ocean, creating conditions that favor the emergence and evolution of life. But we need to be honest about the uncertainties. We don't know for certain that K2-18b has an ocean. The planet's density suggests it, computer models support it, but we haven't directly observed liquid water on the surface. The ocean world hypothesis is our best explanation for the data, but it's still a hypothesis. Future observations might test this idea. If the planet has a deep ocean, its atmosphere should show specific patterns of water vapor distribution. The way the planet reflects light could reveal whether a liquid surface exists. Webb and future telescopes might be able to distinguish between a planet with a surface ocean and one that's just a thick atmosphere all the way down. The ocean world hypothesis transforms K2-18b from an interesting exoplanet into a potential cradle for life. If confirmed, it would prove that habitable environments can exist in configurations we never imagined. Deep water worlds wrapped in hydrogen, warmed by their own chemistry, potentially teeming with alien biology beneath alien skies. K2-18 is not a star like our sun. It's a red dwarf, smaller, cooler, dimmer, and far more temperamental. But this seemingly modest star might be the most important type of star in the galaxy when it comes to understanding where life can exist, because red dwarfs have one extraordinary advantage: time. Our sun has a lifespan of about 10 billion years total. It's currently middle-aged at 4.6 billion years old. In another 5 billion years, it will exhaust its hydrogen fuel, expand into a red giant, and incinerate Earth. Any life that evolves in our solar system has this cosmic deadline, roughly 5 billion years before the sun destroys everything. Red dwarfs operate on a completely different timescale. K2-18 could burn steadily for 70 to 100 billion years, 7 to 10 times longer than the current age of the universe. Some red dwarfs might shine for 1 trillion years. This isn't hyperbole, it's basic stellar physics. Smaller stars burn their fuel more efficiently and live proportionally longer. This matters profoundly for life. On Earth, simple single-celled organisms appeared relatively quickly, within 1 billion years of the planet forming. But complex multicellular life took nearly 4 billion years to evolve. Intelligence required almost the full 4.6 billion year history of Earth. Evolution needs time, and red dwarfs provide time in almost unlimited quantities. If K2-18b has life, and if that life has been evolving for even a few billion years, it could have reached levels of complexity that Earth's biosphere won't achieve for eons. The organisms producing those atmospheric biosignatures might be far more sophisticated than anything in our oceans. But red dwarfs come with significant challenges. They're prone to stellar flares, massive eruptions that can temporarily increase the star's energy output by factors of 10 or even 100. These flares blast nearby planets with radiation that could strip away atmospheres and sterilize surfaces. Young red dwarfs are especially violent, experiencing frequent superflares that would be catastrophic for any emerging life. K2-18 appears to be a relatively well-behaved red dwarf. Observations show minimal flare activity, though astronomers haven't monitored it long enough to rule out occasional violent outbursts. The planet's thick hydrogen atmosphere could provide crucial protection, acting as a shield that absorbs and deflects radiation that would otherwise reach the surface or ocean. The star's spectrum creates another challenge. Red dwarfs emit most of their energy in infrared wavelengths, with relatively little visible light. Plants on Earth use visible light for photosynthesis, capturing energy in the blue and red portions of the spectrum. On K2-18b, any photosynthetic organisms would need to evolve completely different light harvesting systems, optimized for infrared rather than visible wavelengths. But this isn't necessarily a deal breaker. Some bacteria on Earth can perform photosynthesis using infrared light. They use different pigments and different biochemical pathways than plants, proving that infrared photosynthesis is possible. Life on K2-18b might have taken this strategy and run with it, creating entire ecosystems based on harvesting infrared energy. The tidal locking adds another variable. K2-18b completes one orbit every 33 days, and it's locked so that one side always faces the star. The day side receives constant infrared radiation. The night side exists in perpetual darkness. On Earth, this would create temperature extremes, a scorching day side and a frozen night side. But K2-18b's thick atmosphere could redistribute heat, creating a twilight zone around the terminator where conditions might be especially favorable for life. Red dwarfs make up about 75% of all stars in the Milky Way. If their planets can host life despite the challenges, then the number of potentially inhabited worlds in our galaxy increases from millions to tens of billions. Every red dwarf star becomes a candidate for hosting living worlds. This is why K2-18b matters so much. It's not just one potentially habitable planet, it's proof of concept that the most common stars in the galaxy can support life. If the biosignatures on K2-18b are confirmed, it suggests that red dwarf systems are viable homes for biology. The galaxy suddenly becomes far more crowded with life than we ever imagined. Time is the ultimate resource for evolution, and red dwarfs have time to spare. K2-18b is 120 light-years away. That distance is both impossibly vast and tantalizingly close. It represents the fundamental paradox of exoplanet science. We can detect chemical signatures of potential life across interstellar space, but we can never visit these worlds to confirm what we're seeing. To understand this distance, imagine shrinking the Milky Way galaxy to the size of North America. Earth would be smaller than a grain of sand. K2-18b would be another grain of sand about the width of a small town away. In a galaxy containing over 100 billion stars, K2-18b is practically next door, yet completely unreachable with current technology. Light from K2-18b takes 120 years to reach us. The photons Webb detected left that world in 1904, when the Wright brothers were still perfecting powered flight. If there are organisms on K2-18b producing dimethyl sulfide, they created those molecules when Teddy Roosevelt was president of the United States. We're literally seeing the past, observing the chemical breath of life from over a century ago. This time delay creates a profound philosophical question. What are we actually detecting? If life existed on K2-18b 120 years ago, does it still exist today? Could that biosphere have collapsed in the time it took for light to reach us? We have no way of knowing. We're observing a snapshot frozen in time while the actual planet has moved on through 120 years we can't see. The distance also makes confirmation extraordinarily difficult. Our fastest spacecraft, Voyager 1, travels at about 38,000 miles per hour, an impressive speed by human standards but glacial on cosmic scales. At that velocity, it would take over 2 million years to reach K2-18b. No human civilization in history has maintained continuity for even 10,000 years. A mission to K2-18b is beyond not just our current technology, but our capacity for sustained multi-generational planning. Yet that same distance makes the detection even more remarkable. If Webb can identify biosignatures on K2-18b from 120 light-years away, the biological activity must be enormous. We're not detecting isolated pockets of microbes. We're detecting planetary-scale processes that have fundamentally altered atmospheric chemistry. The organisms producing these signatures aren't just surviving, they're thriving with such abundance that their collective metabolism is visible across interstellar space. The 120 light-year distance places K2-18b within what astronomers call the solar neighborhood, a sphere of space containing several thousand stars. If life exists on K2-18b at this distance, statistical arguments suggest our local galactic neighborhood might be crowded with living worlds. Within 1,000 light-years, there could be hundreds of biologically active planets. Within 10,000 light-years, potentially millions. But distance also imposes limits on what we can learn. Webb can detect molecules, measure temperatures, and analyze atmospheric composition. But it can't resolve surface features. It can't see oceans, continents, or ecosystems. It can't detect individual organisms or observe behavior. Everything we know about K2-18b comes from analyzing starlight. We're reading a chemical message written across the void, interpreting meaning from molecular signatures. Future telescopes might overcome some of these limitations. The proposed Habitable Worlds Observatory could potentially detect oxygen, methane, and other biosignatures with much greater sensitivity. Next-generation instruments might even be able to measure seasonal variations in atmospheric chemistry, watching a planet's biosphere respond to changing conditions in real time despite the vast distance. There's also a stranger possibility. If intelligent life exists on K2-18b, our radio signals are just now reaching their world. We've been broadcasting radio and television into space for about 120 years, and that bubble of electromagnetic noise is expanding outward at the speed of light. K2-18b sits right at the edge of that bubble. If anyone there is listening, they might be hearing Earth's first radio transmissions right now. The distance to K2-18b reminds us that the universe is unimaginably vast, but also that our technological reach is growing. We can't visit this world, but we can study it. We can learn from it. We can use it to understand how common life is in the cosmos. Sometimes, seeing from a distance is enough to change everything. The 99.7% confidence level has become the headline. But what does it actually mean? In science, certainty is measured in standard deviations called sigma. A 3 sigma detection means there's only a 0.3% chance, 3 in 1,000, that the signal is random noise. It's the same threshold used to discover the Higgs boson and detect gravitational waves. But here's the critical distinction that often gets lost. The 99.7% confidence applies to whether there's a real signal in the data, not to what that signal actually is. Webb definitively detected something absorbing light at specific infrared wavelengths. The statistical confidence that this absorption feature is real, not instrumental noise, is extremely high. But identifying what molecule is causing that absorption is a different challenge entirely. Think of it like hearing a sound in the dark. You can be 99.7% certain you heard something. That's the statistical confidence in the signal. But determining whether it was a footstep, a tree branch, or the house settling requires interpretation. That's where the scientific debate centers. The spectroscopic signature appears at wavelengths where dimethyl sulfide absorbs infrared light. But other molecules absorb light at similar wavelengths. Carbon disulfide, for example, creates spectral features that overlap with dimethyl sulfide. Distinguishing between them requires exceptionally high-resolution data and careful analysis of multiple absorption lines. The signal-to-noise ratio adds another layer of complexity. Webb is detecting absorption features that represent tiny fractions of the total light from K2-18. The actual change in brightness is measured in parts per million. Extracting a genuine molecular signature from this faint signal requires sophisticated statistical techniques and exhaustive testing for systematic errors. Multiple research. Teams are using different analysis methods on the same data and reaching different conclusions. Some find strong evidence for dimethyl sulfide, others argue the signal is too ambiguous to identify confidently. A few suggest the spectral features are better explained by a combination of other molecules. This isn't a failure of science, it's science working exactly as it should, with multiple groups independently analyzing data and debating interpretations. The Bayesian approach to the statistics adds nuance. Even if the dimethyl sulfide spectral feature is real with 99.7% confidence, we also need to consider prior probabilities. How likely is it that life exists on K2-18b in the first place? If we assume life is rare, then even a strong signal might be more likely explained by unknown chemistry. If we assume life is common, the same signal becomes more compelling evidence for biology. This is where the Drake equation thinking enters. Our interpretation of the data depends partly on our assumptions about how common life is in the universe. It's a circular problem. We're trying to use K2-18b to determine if life is common, but our interpretation of K2-18b depends on whether we think life is common. The follow-up observations become crucial. If future Webb observations consistently detect the same spectral features, confidence increases. If the signal appears in some observations but not others, it might be instrumental noise or variable atmospheric conditions. If multiple molecules pointing to biology are detected together, dimethyl sulfide plus other biosignatures, the case strengthens dramatically. Some researchers are calling for observations during multiple transits across different seasons of K2-18b's 33-day year. If the biosignature varies with time, that could indicate biological cycles responding to changing conditions, much stronger evidence for life than a constant signal that could be explained by stable chemistry. Laboratory work is also crucial. Scientists are creating hydrogen-rich atmospheres in the lab, testing how dimethyl sulfide and similar molecules behave under exotic conditions. These experiments will help determine whether the molecule can form through non-biological processes under K2-18b's atmospheric conditions. The statistical battlefield is where the real science happens. It's messy, contentious, and filled with legitimate disagreement. But this process of challenge, replication, and debate is how we move from intriguing possibility to confirmed discovery. The 99.7% is just the beginning of the conversation, not the end. Science advances by eliminating wrong answers. Before we can claim we've found life on K2-18b, we need to systematically rule out every non-biological explanation for what Webb detected. This is where the real work begins. The first alternative is straightforward misidentification. The spectral feature attributed to dimethyl sulfide could be caused by a different molecule entirely. Carbon disulfide is the prime suspect. It's chemically similar and creates absorption features at overlapping wavelengths. Unlike dimethyl sulfide, carbon disulfide can form through volcanic activity and other geological processes. If the signal is actually carbon disulfide, the biosignature interpretation collapses. Then there's the possibility of instrumental artifacts. Webb's instruments are extraordinarily sensitive, but that sensitivity comes with challenges. The telescope's mirrors, filters, and detectors all interact with light in complex ways. Sometimes these interactions create false signals that mimic real molecular absorption. Multiple research teams are analyzing the raw data to determine whether the dimethyl sulfide feature could be an artifact of how Webb processes infrared light. Atmospheric chemistry under exotic conditions offers another escape route. K2-18b's hydrogen-rich atmosphere creates chemical environments we can't replicate on Earth. Reactions that are impossible in our atmosphere might be commonplace there. Some researchers propose that dimethyl sulfide could form through purely chemical processes involving hydrogen, methane, and sulfur compounds under the high pressures and temperatures of K2-18b's atmosphere. Laboratory experiments are testing this hypothesis. Scientists are creating miniature versions of K2-18b's atmosphere in pressure chambers, mixing hydrogen, methane, water vapor, and sulfur compounds, then exposing them to ultraviolet radiation and temperature variations. If dimethyl sulfide forms in these experiments without any biological input, it would prove the molecule isn't necessarily a biosignature on this type of world. There's also the contamination question. Could the signal be contaminated by Earth's own atmosphere or by molecules in our solar system? Webb orbits at L2 beyond Earth's atmosphere, minimizing this risk. But cosmic rays, zodiacal dust, and other factors can introduce noise into astronomical observations. Careful calibration and multiple observations help rule out contamination, but it remains a consideration. Some scientists point to the methane as the real puzzle. Methane on K2-18b could be explained by geological processes, volcanic outgassing from the planet's interior, chemical reactions in the deep ocean, or delivery by comets and asteroids. If methane doesn't require biology, then the atmospheric chemistry might be entirely abiotic, even if it looks superficially biological. The stellar contamination hypothesis suggests that features in the star's own spectrum could be creating false signals when we analyze the planet's atmosphere. K218 is an active red dwarf with surface features like star spots, cooler regions that appear dark against the stellar surface. When the planet transits, it might preferentially block light from certain parts of the star, creating spectral distortions that mimic molecular absorption in the planet's atmosphere. There's also the argument from complexity. Life as we know it requires incredibly specific conditions and chemistry. The odds that life emerged independently on K218b, a world radically different from Earth, might be astronomically small. By this reasoning, any alternative explanation, no matter how contrived, is more likely than biology. But this argument cuts both ways. If life can only emerge in Earth-like conditions, finding biosignatures on such an alien world would be extraordinarily significant. It would prove that biology isn't restricted to Earth twins, but can emerge across a wide range of planetary environments. The scientific method demands we take alternative explanations seriously. Each one needs to be tested, analyzed, and either confirmed or ruled out. This process takes time, years of additional observations, laboratory experiments, and theoretical modeling. It's frustrating for those eager to declare, "We've found life, but it's essential for getting the answer right." What's encouraging is that the alternatives are testable. If the signal is carbon disulfide instead of dimethyl sulfide, higher resolution spectroscopy will reveal additional absorption features that distinguish the two molecules. If it's an instrumental artifact, it won't appear consistently across multiple observations. If it's exotic atmospheric chemistry, laboratory experiments will demonstrate the formation pathway. The existence of alternative explanations doesn't diminish the discovery, it focuses the investigation. We now know exactly what questions to ask and what observations to make. The next phase of research will systematically test each alternative until only one explanation remains standing. K218b might belong to an entirely new category of planet that didn't exist in our vocabulary until a few years ago. Astronomers call them Hycean worlds, planets with hydrogen atmospheres and ocean surfaces. The name combines hydrogen and ocean, describing environments so alien that we're still figuring out if they can support life at all. The Hycean concept emerged from a simple question: what happens to a planet that's too small to be Neptune but too large to be Earth? Traditional planetary models suggested these worlds would be mini-Neptunes, gas-rich planets with no solid surface and no prospects for life. But computer models revealed a more interesting possibility. If such a planet formed far enough from its star to accumulate massive amounts of water ice, then migrated inward to the habitable zone, the ice would melt. The result would be a deep liquid ocean beneath a hydrogen-rich atmosphere, a Hycean world. K218b's mass, density, and atmospheric composition all fit this profile. The Hycean environment creates conditions unlike anything in our solar system. The atmospheric pressure at the ocean surface could be hundreds of times greater than Earth's sea level pressure. The hydrogen atmosphere would extend thousands of miles above the ocean, creating a gradual transition from liquid water below to hydrogen gas above, with no clear boundary between ocean and sky. This changes the rules for habitability. On Earth, life exists in a thin shell, a few miles of ocean depth, a few miles of atmosphere, and the surface in between. Hycean worlds offer a much larger habitable volume. The ocean could be hundreds of miles deep. The atmosphere extends even higher. Any life that emerged could potentially occupy this vast three-dimensional space. The chemistry of Hycean worlds opens up possibilities that don't exist on Earth. Hydrogen dissolving into the ocean creates a reducing environment, one where chemical reactions run in reverse compared to Earth's oxygen-rich oceans. Organisms in this environment might use hydrogen as their primary energy source, combining it with carbon dioxide to produce methane and water in a metabolic pathway completely different from anything in Earth's biosphere. Temperature stratification in a Hycean ocean could create multiple habitable zones. The deep ocean, heated by the planet's interior, might be hot enough to drive rapid chemistry. The mid-depths could offer more moderate temperatures, ideal for complex organisms. The surface, cooled by radiation to space, might be the coldest zone, but still warm enough for liquid water if the atmospheric greenhouse effect is strong enough. The tidal locking of K2-18b adds another dimension. The day side receives constant stellar radiation, potentially driving photochemistry in the upper atmosphere and surface waters. The night side exists in darkness, but the ocean's thermal inertia and atmospheric circulation could keep temperatures habitable. Time doquans The twilight zone between eternal day and eternal night might be the sweet spot, neither too hot nor too cold, with enough light to drive photosynthesis, but not so much that radiation becomes harmful. But Haitian worlds face significant challenges. The high atmospheric pressure could make it difficult for complex molecules to maintain their structure. The lack of a solid surface raises questions about how life could originate. On Earth, mineral surfaces and tidal pools played crucial roles in prebiotic chemistry. The hydrogen atmosphere might be too reducing to allow the oxygen-dependent biochemistry that powers complex life on Earth. Some researchers argue that Haitian worlds are inherently unstable. The hydrogen atmosphere might slowly erode away under stellar radiation, or the ocean could gradually freeze as the planet loses internal heat. Others counter that these worlds could maintain habitable conditions for billions of years if they're massive enough and orbit at the right distance. The Haitian concept also raises questions about detection. If life exists on these worlds, what biosignatures would it produce? Dimethyl sulfide might be one, but hydrogen-breathing organisms might generate molecules we wouldn't think to look for. We might be missing entire categories of biosignatures because we're searching for chemistry familiar from Earth. K2-18b might be the first confirmed Haitian world, or it might turn out to be something else entirely. But the concept has already changed how astronomers think about habitability. We're no longer limited to searching for Earth twins. We can now imagine and search for entire classes of worlds where life might emerge through pathways we're only beginning to understand. Methane shouldn't persist in K2-18b's atmosphere. This simple molecule, one carbon atom surrounded by 4 hydrogen atoms, is chemically unstable. In most atmospheric conditions, it reacts with other gases. It breaks down under ultraviolet radiation. Yet Webb detected substantial amounts of methane wrapped around this distant world. Something is producing it faster than natural processes can destroy it. On Earth, methane tells an almost exclusively biological story. Wetland bacteria generate about 150 million tons annually. Rice paddies produce another 40 million tons, thanks to microorganisms in flooded soil. Livestock contribute significantly through digestive processes. Natural geological sources exist. Volcanic vents, gas seeps from deep underground, but they're minor compared to biological production. The methane on K2-18b appears in concentrations high enough to affect the planet's atmospheric chemistry. If this were a small amount, you could wave it away as geological outgassing or cometary delivery. But the signal Webb detected suggests ongoing active production. Either the planet has extraordinarily vigorous geological activity, or something biological is pumping methane into the atmosphere. The hydrogen-rich environment changes the methane equation. On Earth, methane is a trace gas making up less than 2 parts per million of our atmosphere. On K2-18b, methane exists alongside vast quantities of hydrogen. This creates chemistry that's impossible to study on Earth because we can't replicate those conditions in the laboratory. Some researchers propose that methane could form through serpentinization, a geological process where water reacts with iron-rich rocks to produce hydrogen, which then combines with carbon dioxide to create methane. This happens on Earth in deep ocean hydrothermal vents, and it's completely abiotic. If K2-18b has similar geology, it could generate methane without any biological involvement. But there's a problem with the geological explanation. Serpentinization requires specific rock types and active geological processes. We don't know if K2-18b has the right conditions. Computer models of the planet's interior suggest it might have a high-pressure ice mantle rather than exposed rock, which would limit serpentinization. The methane source remains puzzling. The presence of methane alongside carbon dioxide creates another intriguing pattern. On Earth, these two gases are intimately connected through biology. Photosynthetic organisms consume CO2 and release oxygen. Other organisms produce methane. The balance between these gases helps regulate Earth's climate. K2-18b shows similar coexistence, raising the question of whether biological processes are maintaining this chemical balance. Methane also interacts with the dimethyl sulfide question. If organisms on K2-18b are producing methane through metabolic processes, they might also be producing sulfur-containing molecules as byproducts. The two signatures together strengthen the biological interpretation more than either would alone. Multiple biosignatures detected simultaneously become much harder to explain through chemistry alone. The atmospheric lifetime of methane on K2-18b is uncertain. On Earth, methane persists for about a decade before breaking down. But K2-18b's hydrogen-rich atmosphere might slow or accelerate this process. If methane is more stable there, you'd need less production to maintain the observed concentrations. If it's less stable, the required production rates would be even higher. Future observations could test the methane hypothesis by looking for isotopic signatures. Biological methane on Earth has a characteristic ratio of carbon-12 to carbon-13 that differs from geological methane. If Webb's successor instruments can measure these ratios on K2-18b, they might be able to distinguish between biological and geological sources definitively. There's also the seasonal variation question. If methane production is biological, it might vary with planetary conditions, perhaps showing cycles tied to the planet's 33-day orbit or longer climate patterns. Geological methane should be relatively constant. Monitoring K2-18b over multiple years could reveal whether the methane signal changes in ways consistent with living processes. The methane mystery illustrates how every piece of data raises new questions. We've detected the molecule, measured its abundance, and confirmed it's really there. But understanding what it means requires untangling complex chemistry, ruling out alternative explanations, and gathering more observations. The methane isn't proof of life, but it's a compelling piece of a larger puzzle. If life exists on K2-18b, it won't look like anything on Earth. The conditions are too alien, the environment too different. But we can make educated guesses based on chemistry, physics, and the principles of natural selection. Start with the ocean. If K2-18b has the deep global ocean that models suggest, life might have originated in hydrothermal vents on the ocean floor, the same environment where some scientists think Earth's life began. These vents would pour mineral-rich, energy-laden water into the surrounding ocean, creating chemical gradients that simple organisms could exploit for energy. The first life forms would almost certainly be microscopic, single-celled organisms adapted to high-pressure, hydrogen-rich water, and complete darkness in the deep ocean. These primordial organisms might metabolize hydrogen, combining it with carbon dioxide to produce methane and extract energy, a process called methanogenesis that's ancient on Earth but could be the dominant metabolic pathway on K2-18b. As life evolved, some organisms might have migrated upward through the ocean column, following the chemical gradients and energy sources. In the mid-depths, where pressure is lower and dissolved gas is more abundant, larger organisms could emerge. Without hard surfaces to anchor to, these creatures might be free-floating, drifting through the water column, harvesting hydrogen and methane, perhaps forming complex colonies. The ocean surface presents different challenges and opportunities. Here, infrared light from K2-18 penetrates the hydrogen atmosphere and reaches the water. Organisms might evolve infrared photosynthesis, using pigments completely different from Earth's chlorophyll to capture long wavelength light and convert it into chemical energy. These photosynthesizers would form the base of a food web, supporting more complex ecosystems, but there's no solid surface, no continents, no islands, no shorelines. Any complex life would need to be adapted to permanent suspension in water. Think of Earth's open ocean, but extending down hundreds of miles with no seafloor within reach. Organisms might evolve buoyancy control mechanisms, gas-filled bladders, or lipid-rich tissues that allow them to float at specific depths. The permanent dayside and nightside create distinct environments. Dayside organisms might be adapted to constant infrared, radiation, perhaps developing protective pigments, or living deeper in the water column to avoid surface conditions. Nightside life would exist in eternal darkness, relying entirely on chemical energy or bioluminescence for any light-dependent processes. The twilight zone, the terminator region where day meets night, might be the most habitable. Here, Angled light from the star provides enough energy for photosynthesis without the harsh conditions of the subsolar point. Atmospheric circulation patterns could create stable currents in this region, concentrating nutrients and supporting dense populations. Intelligence is a wild card. On Earth, complex nervous systems evolve to process sensory information and coordinate movement. On K2-18b, similar pressures might drive the evolution of sophisticated brains. But the forms that intelligence takes could be radically different. Perhaps distributed neural networks and colonial organisms or chemical communication systems we wouldn't recognize as thought. The hydrogen atmosphere itself might be inhabited. On Earth, the upper atmosphere is essentially sterile, too dry, too cold, too exposed to radiation. But K2-18b's thick hydrogen envelope might support floating life forms, perhaps suspended on gas-filled sacs, harvesting methane and water vapor, never touching the ocean below. Any life on K2-18b would need to solve problems that Earth life never faced. How do you build complex structures in high-pressure water with no solid surfaces? How do you evolve sensory systems in an environment dominated by infrared light and chemical signals? How do you develop technology without fire, metalworking, or solid ground to build on? These questions might sound like science fiction, but they're grounded in legitimate biology and chemistry. Life is fundamentally about extracting energy from the environment and using it to maintain organization and reproduction. The specific forms it takes depend on the environment. K2-18b's environment would shape life in directions we can barely imagine. If we confirm biosignatures on K2-18b, the next challenge will be understanding what kind of life is producing them. That might require observations far beyond what current technology can achieve, perhaps eventually sending probes to study this world up close, centuries or millennia from now. K2-18b's mass, 8.6 times greater than Earth, might seem like a disadvantage for life. That crushing gravity, those extreme pressures. But planetary scientists are discovering that bigger might actually be better when it comes to long-term habitability. Earth is slowly dying, not immediately, not catastrophically, but inexorably. Our planet loses about 3 kilograms of hydrogen to space every second. That hydrogen comes from water vapor broken apart by solar radiation in the upper atmosphere. Over billions of years, Earth will lose its oceans and become a desiccated wasteland like Mars. We have perhaps 1 billion years before this process makes Earth uninhabitable. K2-18b's powerful gravity prevents this fate. The stronger gravitational field holds the atmosphere tighter, making it much harder for gases to escape to space. Even the lightest molecules, hydrogen and helium, remain bound to the planet. This means K2-18b can maintain its atmosphere and oceans for potentially trillions of years, far longer than Earth's habitability window. The planet's mass also affects its geological evolution. Earth's interior is cooling, and in a few billion years, our planet will be geologically dead. The magnetic field generated by Earth's liquid iron core will shut down, leaving the surface exposed to solar radiation. Plate tectonics will cease, ending the carbon cycle that regulates our climate. K2-18b's greater mass means more internal heat, potentially maintaining geological activity for periods longer than the current age of the universe. This extended geological activity matters for life. On Earth, plate tectonics drives the carbon cycle, pulling carbon dioxide out of the atmosphere through weathering and returning it through volcanism. This natural thermostat has kept Earth's temperature stable for billions of years. K2-18b's sustained geological activity could provide similar climate regulation over much longer timescales. The planet's size also determines its magnetic field strength. Larger planets with more vigorous internal dynamics can generate stronger magnetic fields. These fields deflect charged particles from the star, protecting the atmosphere from erosion and the surface from harmful radiation. K2-18b likely has a magnetic field substantially stronger than Earth's, providing better shielding for any life that might exist there. There's a thermal advantage too. Larger planets have lower surface area to volume ratios, meaning they radiate heat more slowly. K2-18b retains its primordial heat more efficiently than Earth, potentially providing a stable internal heat source that could last for hundreds of billions of years. This internal heat could drive ocean circulation, maintain hydrothermal systems, and provide energy for chemosynthetic life. The mass also affects the planet's volatile inventory, the total amount of water, carbon dioxide, and other compounds it can hold. More massive planets can gravitationally capture and retain larger quantities of these essential ingredients for life. K2-18b might have accumulated volatile rich material during its formation, giving it resources that could support biology for eons. But size brings challenges. The higher surface gravity, about 3 times Earth's, would make it difficult for any large organisms to support their own weight. Flight would be nearly impossible. Even swimming would require more energy. Any complex life would need to evolve structural adaptations to handle the crushing gravity. The greater mass also means higher internal pressures. The planet's ocean might be hundreds of miles deep, but the pressure at the bottom would be crushing, millions of times Earth's surface pressure. Only the upper regions of the ocean would be potentially habitable, with the deep ocean possibly too extreme even for extremophile organisms. The super-Earth category represents a sweet spot in planetary science. These worlds are large enough to maintain thick atmospheres and deep oceans over cosmic timescales, but not so large that they become gas giants like Jupiter. They're massive enough to retain volatiles and maintain geological activity, but not so massive that surface conditions become uninhabitable. And here's the remarkable thing: super-Earths are common. They're the most frequently detected type of exoplanet in the galaxy. If these worlds can support life despite their alien conditions, then habitable planets might outnumber Earth-like worlds by 10 to 1 or even 100 to 1. The galaxy could be filled with super-Earth biospheres, each taking advantage of the long-term stability that greater mass provides. Webb's observations of K2-18b represent just the opening chapter. The next decade will bring increasingly powerful instruments capable of testing the biosignature hypothesis with unprecedented precision. The technology to definitively answer whether life exists on this world is already being built. The immediate priority is more Webb observations. Astronomers have requested additional transit observations across multiple wavelengths, targeting specific spectral features that can distinguish dimethyl sulfide from similar molecules. These observations will also search for other potential biosignatures, phosphine, ammonia depletion, or organic hazes that could strengthen the case for biology. The extremely large telescope in Chile represents the next leap forward. With a mirror over 100 feet across, nearly 5 times larger than Webb's, the ELT will collect vastly more light and achieve higher spectral resolution. It could potentially detect dozens of different molecules in K2-18b's atmosphere, building a complete chemical inventory that reveals whether the planet's chemistry is biological or abiotic. The ELT's ground-based location creates challenges. Earth's atmosphere interferes with observations. But adaptive optics technology can compensate using deformable mirrors that adjust thousands of times per second to cancel out atmospheric turbulence. The result is clarity that rivals space-based telescopes for certain types of observations. NASA's proposed Habitable Worlds Observatory represents the ultimate tool for exoplanet biosignatures. This space telescope, planned for launch in the 2040s, is being designed specifically to find and characterize Earth-like planets around Sun-like stars. While K2-18b isn't its primary target, the HWO could observe this world, with sensitivity far exceeding Webb's, potentially detecting faint biosignatures that current instruments can't reach. The HWO will use a starshade, a giant flower-shaped screen that flies in formation with the telescope, positioned to block starlight while allowing light from orbiting planets to pass. This technology could achieve contrast ratios of 10 billion to 1, making even faint biosignatures detectable. For K2-18b, this could mean identifying complex organic molecules or detecting seasonal variations in atmospheric chemistry. Closer to the present, the European Space Agency's Ariel mission will launch in 2029 to study exoplanet atmospheres. While primarily focused on hot Jupiters and other well-studied worlds, Ariel could observe K2-18b during its survey phase, providing independent confirmation of Webb's findings and searching for atmospheric variations over time. The real breakthrough might come from coordinated observations using multiple instruments simultaneously. Webb observes in infrared. The ELT can work in visible and near-infrared wavelengths. Radio telescopes can search for molecular emission lines. Combining these different perspectives creates a three-dimensional view of the planet's atmosphere that no single instrument could provide. Laboratory work will advance in parallel. Scientists are developing better models of how molecules behave in hydrogen-rich atmospheres under high pressure. They're creating experimental setups that mimic K2-18b's conditions, testing whether dimethyl sulfide and other biosignatures can form abiotically. These experiments will either strengthen the biological interpretation or reveal alternative chemical pathways. Machine learning algorithms are being trained to recognize biosignatures in noisy, spectroscopic data. These AI systems can analyze thousands of spectral features simultaneously, identifying patterns that human researchers might miss. They could potentially detect subtle combinations of molecules that together constitute stronger evidence for life than any single biosignature. The timeline matters. Each new observation requires careful planning. Transit events only happen every 33 days, and Webb's schedule is overbooked with targets. Priority access requires convincing review committees that the observations are worth the telescope time. But the scientific community recognizes K2-18b's importance, and follow-up observations are being prioritized. Within 5 years, we should have much clearer answers. If the dimethyl sulfide detection holds up across multiple observations and techniques, confidence will increase dramatically. If additional biosignatures are detected, the case for life becomes overwhelming. If the signal disappears or proves to be misidentified, we'll redirect our attention to other promising targets. The next generation of observations will do more than just study K2-18b. They'll establish protocols for detecting and confirming biosignatures on exoplanets, creating a roadmap for investigating hundreds of potentially inhabited worlds. K2-18b is the test case that's teaching us how to find life in the cosmos. If life exists on K2-18b, it fundamentally changes the Fermi paradox. The question of why, if life is common, we haven't detected any signs of intelligent civilizations. The paradox assumes that technological civilizations should be obvious, broadcasting radio signals or leaving visible traces of their activity. K2-18b suggests a different possibility. Enrico Fermi's famous question, "Where is everybody?" assumes that intelligent life would develop technology and spread across the galaxy. Given the age of the universe and the number of potentially habitable planets, Earth should have been visited or colonized long ago. Yet we see no evidence of extraterrestrial civilizations. This apparent contradiction has puzzled scientists for decades. K2-18b offers a potential resolution. Perhaps life is common, but technological civilizations are rare. If biology can emerge on hydrogen-rich super-Earths orbiting red dwarf stars, then the galaxy might be teeming with microbial life, complex ecosystems, even intelligent organisms, but very few spacefaring civilizations. The environment on K2-18b illustrates why. There's no solid surface to build on, no access to fire for metallurgy. The high surface gravity makes escaping the planet's gravity well extraordinarily difficult. Any intelligent species that evolved there would face enormous obstacles to developing technology. They might be intelligent, communicative, even self-aware, but unable to build radio telescopes or spacecraft. This suggests a filter in the development of civilizations. Life might be common, but the specific conditions that allow technological development, solid surfaces, moderate gravity, accessible metal ores, atmospheric oxygen for fire, might be rare. Earth might be unusual not because it has life, but because it has the conditions that allow life to develop technology. The statistical implications are profound. If super-Earths around red dwarf stars can host life, the number of inhabited worlds in the galaxy jumps from millions to billions. But if only a tiny fraction of those worlds can support technological civilizations, the number of spacefaring species might still be small. The galaxy could be alive but largely silent. There's another possibility. Perhaps technological civilizations develop but don't last long. They might destroy themselves through war, environmental collapse, or other catastrophes before spreading beyond their home systems. If the typical lifetime of a technological civilization is just thousands of years, a blink in cosmic time, then even if many arise, few would exist at any given moment to communicate with us. K2-18b might also suggest that we're looking for the wrong signals. If most intelligent life evolves in oceans under thick atmospheres, they might never develop radio technology. Their communication might be chemical, acoustic, or bioluminescent, signals we wouldn't think to search for and couldn't detect across interstellar distances even if they existed. The ocean world bottleneck hypothesis proposes that while ocean worlds might be ideal for life, they're terrible for developing civilization. Intelligent octopi or dolphins might evolve, but without the ability to create fire, work metal, or access space, they remain confined to their oceans. Earth's combination of oceans and land might be the rare configuration that allows both the origin of life and the development of technology. There's also the time factor. Red dwarf stars burn for trillions of years, but they're also young compared to the universe's age. Most red dwarfs are still relatively young, and their planets might not have had time to evolve complex life yet. We might be early, one of the first technological civilizations to arise in a galaxy that will eventually teem with spacefaring species. The Great Filter concept suggests that there's some stage in the development from chemistry to spacefaring civilization that's extremely difficult to pass. If the filter is behind us, perhaps the origin of life itself, then the galaxy might be full of living worlds. If it's ahead of us, perhaps nuclear weapons or artificial intelligence, then most civilizations might not survive to spread across the stars. K2-18b forces us to confront these possibilities. If we confirm life there, we'll know that biology can emerge on worlds radically different from Earth. But we still won't know if intelligence is common, if technology is achievable, or if civilizations survive long enough to communicate. The detection of life on K2-18b would answer one question while raising dozens more about our place in a living cosmos. K2-18b isn't the only world showing hints of potential biosignatures. Webb and other telescopes have identified a growing catalog of exoplanets with atmospheric chemistry that raises questions about biology. The discovery on K2-18b is part of a larger pattern that's reshaping our understanding of life's distribution in the galaxy. TRAPPIST-1e, a rocky planet orbiting an ultra-cool dwarf star just 40 light-years away, shows intriguing atmospheric features. Early Webb observations detected carbon dioxide, and future observations will search for oxygen, methane, and other potential biosignatures. If TRAPPIST-1e has life, it would prove that biology can emerge on planets even smaller and cooler than K2-18b. Proxima Centauri b, the nearest exoplanet to Earth, at just 4.2 light-years, remains enigmatic. We know it orbits in the habitable zone of the closest star to our Sun, but its host star's violent flare activity raises questions about whether life could survive there. Future observations will search for atmospheric signatures that could reveal whether this neighboring world is habitable or hostile. LHS 1140b represents another promising candidate. This super-Earth orbits a quiet red dwarf and might have conditions similar to K2-18b, potentially a Hycean world with a thick atmosphere and deep ocean. Webb observations are planned to analyze its atmospheric composition and search for biosignatures similar to those tentatively detected on K2-18b. TOI 700D, discovered by NASA's TESS mission, orbits in the habitable zone of a small red dwarf star. It's roughly Earth-sized, and computer models suggest it could have conditions ranging from a Venus-like hothouse to an Earth-like temperate world. Webb observations could determine which scenario is correct and search for signs of biological activity. The catalog also includes worlds where biosignatures would be ambiguous. Venus, in our own solar system, shows phosphine in its atmosphere, a molecule that on Earth is primarily biological. But the extreme conditions on Venus make biological interpretations controversial. The same ambiguity might apply to exoplanets with unusual chemistry. This growing catalog reveals that potentially habitable worlds are diverse. Some are rocky planets like Earth, others are super-Earths like K2-18b. A few might be ocean worlds, ice worlds with subsurface seas, or configurations we haven't even imagined yet. Each requires different observational strategies and raises different interpretative challenges. The statistical analysis of this catalog is telling. Of roughly 5,000 confirmed exoplanets, perhaps 50 to 100 orbit in their stars' habitable zones. Of those, Webb has observed about a dozen in detail. Finding tentative biosignatures on K2-18b after observing just a handful of candidates suggests that either we're extraordinarily lucky or life is more common than even optimistic predictions suggested. But the catalog also reveals how difficult biosignature detection is. Most observations show nothing definitive: atmospheres dominated by hydrogen, or thin atmospheres, or clouds that obscure the surface. K2-18b stands out precisely because its atmospheric chemistry is unusual enough to generate debate. Most worlds are less ambiguous and less interesting. The next decade will expand this catalog dramatically. Webb will observe dozens more potentially habitable worlds. Ground-based telescopes will characterize hundreds of candidates. By 2035, we might have spectroscopic data on every rocky planet within 100 light-years that transits its star. This comprehensive survey will reveal whether K2-18b is unique or representative. Each new entry in the biosignature catalog teaches us something. Negative results, worlds that could support life but show no biosignatures, are as important as positive detections. They constrain how common life is and reveal which types of planets are most likely to host biology. Even ambiguous results narrow the parameter space and guide future observations. The catalog approach also helps address false positives. If we detect similar biosignatures on multiple unrelated worlds, confidence increases that we're seeing real biology rather than exotic chemistry. If biosignatures correlate with specific planetary characteristics, certain masses, certain orbital distances, certain stellar types, that reveals the conditions under which life emerges. K2-18b might be the first entry in a catalog of confirmed living worlds, or it might eventually be reclassified as an ambiguous case. But either way, the systematic survey of potentially habitable exoplanets represents humanity's first serious attempt to map the distribution of life in the galaxy. Detecting life on K2-18b wouldn't be first contact in the traditional sense. No spaceships, no radio messages, no cultural exchange. But it would fundamentally change humanity's philosophical relationship with the universe. We would know with scientific certainty that we're not alone. The implications ripple through every domain of human thought. The philosophical question, are we alone, has haunted humanity since we first looked up at the stars. Every major religion and philosophical tradition has grappled with this question, often reaching different conclusions. The confirmation of life on K2-18b would settle the debate definitively. Life exists elsewhere. The universe is not a vast, sterile wasteland with Earth as the sole exception. This knowledge transforms our cosmic perspective. The Copernican revolution removed Earth from the center of the solar system. Darwin's evolution removed humanity from a special place in biology. The detection of extraterrestrial life would complete this process, removing Earth from any special status in the cosmos. We become one example of life among potentially billions, but it also creates a profound sense of connection. The organisms on K2-18b, if they exist, share something fundamental with us. We're all expressions of the same physical and chemical principles, manifestations of the universe's tendency to organize matter into complex, self-replicating systems. Despite being separated by 120 light-years and evolved under completely different conditions, we're connected by the fact of biology itself. The ethical implications are substantial. If life exists on K2-18b, does it have intrinsic value? Do we have obligations to protect it even if we can never visit? Should we attempt to communicate if we develop the technology or respect whatever form of existence has evolved there? These questions move from theoretical philosophy to practical considerations. Religious and spiritual frameworks would need to integrate this new reality. Some traditions already embrace the possibility of extraterrestrial life. The cosmos is vast and divinity might express itself through multiple forms. Others might struggle to reconcile sacred texts written for a universe centered on Earth. The theological conversations would be as profound as the scientific ones. The psychological impact on humanity would unfold gradually. Initially, there might be excitement, the greatest discovery in history. But as the reality settles in, we'd face an existential adjustment. Every human who ever lived believed either that we were alone or that the question was unanswerable. Suddenly, we'd know the answer. That knowledge changes how we see ourselves and our place in existence. There's also the question of what we do with this knowledge. K2-18b is unreachable with current technology. We can observe it, analyze it, learn from it, but never touch it, never sample it, never know it directly. This creates a new kind of relationship with the cosmos, awareness without access, knowledge without contact. The scientific community would face the challenge of communicating nuance to the public. We've detected tentative biosignatures becomes "we found aliens" in headlines. Managing expectations while maintaining honesty about uncertainties would be crucial. The scientific process requires skepticism and repeated validation, but public understanding often demands simple yes or no answers. Future generations would grow up in a universe known to contain life. Children born after the confirmation would never experience the uncertainty previous generations felt. The question wouldn't be, are we alone? But what else is out there? And will we ever meet them? The psychological baseline of humanity would shift. There's also the question of motivation. Knowing that life exists elsewhere might inspire increased investment in space exploration and astrobiology. Or it might have the opposite effect. If life is common but unreachable, why invest resources in searching for it? The societal response is unpredictable. The detection of life on K2-18b would mark a before and after moment in human history. Everything that came before would be the era when we wondered. Everything after would be the era when we knew. We'd transition from cosmic childhood, naive and alone, to cosmic adolescence, aware of a larger community but not yet able to join it. This philosophical first contact might be more profound than physical first contact. Meeting intelligent aliens would force adaptation and negotiation. But detecting distant microbial or simple life forces us to confront deeper questions about meaning, purpose, and our relationship with the universe itself. Science thrives on uncertainty. The dimethyl sulfide detection on K2-18b sits in that productive space where the data is compelling but not definitive, where multiple interpretations compete, where honest scientists can disagree. This uncertainty isn't a weakness. It's precisely where the most important science happens. Carl Sagan famously said, "Extraordinary claims require extraordinary evidence." The claim that we've detected life on another world is about as extraordinary as claims get. The evidence needs to be overwhelming, unambiguous, and independently verified before the scientific community will accept it. We're not there yet with K2-18b. The current state is best described as tentative detection of a potential biosignature. That's a lot of qualifiers, and they're all necessary. Tentative because multiple research teams haven't yet reached consensus. Potential because alternative explanations haven't been ruled out. Biosignature rather than life because we're detecting molecules, not organisms. This uncertainty creates tension between scientific caution and public interest. Headlines scream, "Life found on alien world," while scientific papers carefully state spectroscopic features consistent with dimethyl sulfide detected, biological origin possible but not confirmed. The gap between these messages reflects different standards of evidence and different tolerance for ambiguity. The history of exoplanet science is littered with premature claims that later collapsed. Biosignatures detected on Venus turned out to be contamination. Atmospheric features on other worlds proved to be instrumental artifacts. The scientific community has learned to be skeptical, to demand multiple independent confirmations, to exhaust alternative explanations before making grand claims. K2-18b could follow this pattern. Further observations might reveal that the spectral feature isn't dimethyl sulfide at all, but a blend of other molecules creating a similar signature. Laboratory experiments might demonstrate abiotic formation pathways under Hisian conditions. The signal might disappear in future observations, proving it was instrumental noise. Or the opposite could happen. Additional observations might strengthen the detection, revealing multiple spectral lines consistent with dimethyl sulfide. Other biosignatures might be detected alongside it. Time series analysis might show variations consistent with biological cycles. The case could become progressively more compelling until skeptics are convinced. The uncertainty also reflects fundamental limits of remote sensing. We're trying to characterize a world 120 light years away using only the tiny fraction of starlight that filters through its atmosphere. The data is inherently noisy, the signals faint, the interpretations ambiguous. We're pushing observational astronomy to its absolute limits. But uncertainty doesn't mean ignorance. We know K2-18b exists. We know its mass, orbital period, and approximate temperature. We know it has a substantial atmosphere containing hydrogen, methane, carbon dioxide, and water vapor. We've detected something absorbing light at wavelengths consistent with dimethyl sulfide. These are facts, even if their interpretation remains debated. The scientific process for resolving uncertainty is clear: more observations, better models, laboratory experiments, and time. Each new data point either strengthens or weakens the biosignature hypothesis. Eventually, perhaps in months, perhaps in years, the uncertainty will resolve. Either the dimethyl sulfide detection will be confirmed and accepted, or it will be explained away and abandoned. Living with uncertainty requires intellectual humility. Scientists must acknowledge what they don't know while clearly stating what they do know. They must resist the temptation to overstate confidence or dismiss possibilities prematurely. The dimethyl sulfide detection is neither confirmed nor refuted. It's an open question being actively investigated. For the public, uncertainty can be frustrating. People want answers. Is there life on K2-18b or not? But science doesn't always provide clean, yes or no answers immediately. Sometimes the honest answer is, we don't know yet, but we're working on it. That's where we are with K2-18b. The uncertainty principle in quantum mechanics states that certain properties of particles cannot be simultaneously known with perfect precision. There's a similar principle in astrobiology. Distant biosignatures cannot be definitively confirmed without either visiting the world or collecting such overwhelming evidence that all alternatives are implausible. K2-18b tests whether we can achieve that level of certainty through remote observation alone. We stand at a unique moment in human history. For the first time, we have the technology to detect potential signs of life on worlds orbiting other stars. K2-18b represents the cutting edge of this capability, a planet where the data is intriguing enough to